Hi, welcome to this course. It is well known that the wise use of control techniques brings many benefits, such as better product and life quality, less waste, less pollution, increased safety, reduced energy consumption, etc. It can be seen that feedback and control concepts play an important role in most socio-technical aspects. The phrase "control will be the physics of the 21st century" means that all engineering students should take an introductory course in systems control. This basis is the foundation of this course, in which complex and extensive calculation and methods are applied with the help of Control System Toolbox in order to carry out all steps of the control engineering investigation of a system. In the industry, you don't have the time to do this calculation yourself, but instead, especially in the automotive and aerospace industries, an approach to validating and verifying system development is the so-called V model, where MathWorks tools or others are used. The Control System Toolbox is a collection of algorithms, mainly written as M files, that implement common techniques of design, analysis, and modeling of control systems. Its wide range of services includes classical and modern methods of control design, including root locus, ball placement, and LQ regulator design. Certain graphical user interfaces simplify the typical tasks of control engineering. This toolbox is built on the fundamentals of Matlab to facilitate specialized control systems for engineering tools. Therefore, the second prerequisite for this course is to have a basic knowledge of Matlab Simulink. For example, the following control system contains a pre-filter F, a plant G, and a controller C, arranged in a single loop configuration. The model also includes a representation of sensor dynamics S. You can represent each of the components as a model object. You do not need to use the same type of model object for each component. For example, represent the plant J as a zero-pole gain model with the double pole at S equals -1, C as a PID controller, and F and S as transfer functions. You can then combine these elements build models that represent your control system or the control system as a whole. For example, create the open loop response SGC. To build a model of the unfiltered closed loop response, use the feedback command. To model the entire closed loop system response from R to Y, combine T with the filter transfer function. The results, open loop, T, and try are also linear model objects. You can operate on them with Control System Toolbox, Control Design, and Analysis command. For example, plot the step response of the entire system. After we have used Control System Toolbox to perform the control engineering calculations and create graphical representation, in the next lectures, we will show the individual steps from setting up the control loop in Simulink to calculating the controller coefficients and designing the required state observers using the DC machine as an electromechanical system. Why the DC machine? There are several reasons. Some say the DC machine is no longer state-of-the-art. No. First of all, there are several industries where this machine is still used, either for cost advantages or for simplicity of control. Speaking of control, the field-oriented control of the synchronous and asynchronous machines is based on the control of the DC machine. You put a few transformations like Park and Clark transformations and some other manipulations to decouple torque and flux, so you get the same control methodology of the DC machine. Often, due to technological circumstances or cost reasons, the speed cannot be measured, but the machine still needs to be speed controlled. Thus, the state observer must be designed to estimate the speed that is no longer measured. After attending this course, you will be able to design all this. So don't hesitate and welcome again to this course.